A moving charge generates a magnetic field. If this charge moves through a magnetic field, then the two fields will interact and the charged particle will feel a force perpendicular to its direction of motion. The direction follows Fleming's left-hand rule. If the particle goes straight through a magnetic field that is going from left to right in front of it, then it will feel a force that makes the particle go down. If you reverse the direction of the magnetic field from right to left, then the particle will curve upwards due to an upward force. The force only exists as long as the charge is inside the magnetic field. If the magnetic field is big enough, the charge will complete a full circle and loop around and around until it runs out of energy. If you have a stronger magnetic field, then the charge will feel a stronger force and so curve more tightly. If the charge is bigger, the same will happen. But if the charge is moving faster, the force will be greater. This relationship is summarized in the equation force equals magnetic flux density times by charge times by velocity of charge. F equals BQV. The faster the charge moves, the bigger the force, but the further the charge will move in a given time. As before, this only works if the magnetic field is perpendicular to the motion of the charge. If it isn't, then we introduce a cos theta element again, where theta is the angle between the plane of motion of the charge and the plane of the magnetic field. The Large Hadron Collider at CERN uses this principle to determine the curvature of its track, given a level of magnetic flux density. It is also used in a cyclotron to generate different types of radiation to study different physical phenomena. One of the most common uses of this principle is in old-style television sets. They have a tube at the back. Magnetic field will be used to deflect electrons onto the correct pixels on the back of the screen, thus producing the desired image on that screen.